No spacecraft has ever reached it. No telescope has ever photographed it. Not Hubble. Not the largest ground-based observatories on Earth. Not the James Webb Space Telescope itself. Scientists have been theorizing about its existence for more than 70 years. And it goes further than that. The Oort Cloud has never been detected by any instrument at all. No image, no signal, nothing. No one has ever seen a single object inside it. We only see them once they fall out. The evidence for its existence is some of the most compelling in modern astronomy. It sounds almost impossible. A structure larger than every planet, every moon, every asteroid combined. Yet we have never actually seen it. But what Webb is beginning to reveal about the objects that travel inward from its depths is quietly rewriting what scientists thought they knew about how the solar system was born. To understand the Oort Cloud, you first have to understand what the solar system looks like from the outside. The planets, the asteroid belt, the Kuiper belt, all of it exists inside a broad flat disk. From above, the solar system would look like a coin. A flat, spinning structure with the sun at the center and everything moving in roughly the same horizontal band. The Oort Cloud is not part of that disk. Astronomers measure vast distances using astronomical units, or AU. 1 AU is the average distance between Earth and the Sun, about 93 million miles. The Oort Cloud is believed to begin at roughly 2,000 astronomical units from the Sun. Rather than forming a flat disk like the planets, it is thought to be a vast spherical shell surrounding the solar system in every direction. To picture that scale, you would have to shrink the entire solar system, every planet, every orbit, down to a single dot at the very center of that shell. And then the numbers become almost impossible to imagine. The outer edge may extend to 100,000 astronomical units. Every planet from Mercury to Neptune fits within 30 astronomical units. The Oort Cloud stretches more than 3,000 times further out than Neptune. At its outermost edge, you are already more than a third of the way to Proxima Centauri, the nearest star to our Sun. From the edge of the Oort Cloud, if you looked back toward the Sun, it would no longer dominate the sky as it does from Earth. It would appear as a brilliant star among countless others. Still one of the brightest, but no longer unique. Inside that shell, scientists believe there may be billions, possibly trillions of icy objects drifting in near-total darkness. Each one moving so slowly that a single orbit around the Sun takes millions of years to complete. No one has ever seen a single one of them. So how can scientists be so sure the Oort Cloud is even there? The answer begins in 1950 with a Dutch astronomer named Jan Oort. Oort was studying long-period comets. These take more than 200 years to complete a single orbit, some taking millions of years. What caught his attention was not where they were going, but where they seemed to have come from. When he calculated their original orbits, they pointed to astonishingly distant starting points. They appeared from every part of the sky. Some from above the flat plane where the planets orbit the Sun, some from below it, and some moving against the direction the planets travel. There was no single source that could explain that distribution. Oort proposed one. A vast spherical reservoir surrounding the solar system. A cloud of icy objects left over from the solar system's formation, disturbed occasionally by the gravitational pull of passing stars or the slow tidal influence of the Milky Way itself. When one of those distant objects gets nudged inward, it begins the long fall toward the Sun. Hundreds of thousands of years later, it appears in our inner solar system as a long-period comet, arriving from whatever direction it happened to be drifting. Every long-period comet crossing our sky is in this interpretation a messenger. Not just a beautiful object, It's a piece of the early solar system drifting through almost complete darkness for billions of years before finally passing close enough for us to study. The question was whether those messengers could tell us anything meaningful about where they came from. That question changed when Webb launched. The James Webb Space Telescope was not designed to study the Oort Cloud. It cannot photograph it. The objects out there are too cold, too dark, too widely separated, and too far from the Sun for any existing instrument to resolve. Even Webb's extraordinary sensitivity cannot detect individual Oort Cloud objects in the cloud itself. But here is what Webb can do instead. When a long-period comet falls toward the Sun and begins to warm, frozen material on its surface starts turning directly into gas, a process called sublimation. Some of that frozen material turns to gas easily. Other kinds need far more warmth to escape. As the gas streams away, it carries dust and organic molecules with it, forming a glowing cloud around the comet's solid core or nucleus. Astronomers call that cloud the coma. Together, the gas and dust carry chemical information, a fingerprint of what the comet is made of, hidden inside its light. Webb reads those fingerprints. Using infrared spectroscopy, Webb splits incoming light into thousands of individual wavelengths. Every molecule interacts with light differently, each one absorbing light at its own specific wavelengths. By mapping which wavelengths are present or absent in a comet's spectrum, Webb can determine what the comet contains without ever touching it. Think of it like reading the ingredients list on a container, except the container is an object the size of a small town, traveling at tens of miles per second, and the ingredients list is written in light. And what those fingerprints are revealing, nobody expected. The object that demonstrated what this approach could achieve was already in the data before Webb launched. C/2014 UN-271, better known as Bernardinelli Bernstein, was identified by astronomers Pedro Bernardinelli and Gary Bernstein, while searching through years of archival images from the Dark Energy Survey. What initially appeared as a faint moving point turned out to be the largest comet nucleus ever measured, estimated at approximately 85 miles across. For comparison, the nuclei of most well-studied comets measure only about 0.6 to 6 miles across. Bernardinelli Bernstein is roughly the size of a small town. The first signs of its activity appeared while the comet was still out beyond Uranus, and at that distance it should have been frozen solid. But the comet was already venting gas and dust. Normally, that kind of activity begins when sunlight warms the comet enough for water ice to turn directly into gas, carrying dust away with it. Water ice requires proximity to the sun, warmth that simply does not exist that far out. Something else was driving the activity. Observations with ALMA, a powerful network of radio telescopes in Chile, detected jets of carbon monoxide, a far more volatile compound that can turn into gas at much greater distances from the sun. That finding raised an immediate question. If carbon monoxide activity is happening this far from the sun, what does that suggest about the chemistry of objects still sitting out in the cloud itself? This comet is a messenger carrying a 4 billion-year-old record. Webb is learning to read it. If this were just one comet, it could have been an anomaly. It wasn't. Recent JWST observations captured a second long-period comet, C/2024 E1 Vierchos, while the comet was still approximately 7 astronomical units from the Sun, beyond the orbit of Jupiter. Even at that distance, Webb found water ice in the comet's coma. But out there, water ice stays frozen solid. It can't be what's driving the activity. Something more volatile was. Carbon dioxide gas, escaping from the surface. The surprise wasn't what Webb detected, It was what it didn't. Alongside water ice and carbon dioxide, there was no sign of carbon monoxide, even though carbon monoxide turns to gas at even lower temperatures and should have escaped first. Its absence suggests the comet may have lost its near-surface carbon monoxide very early in its history, before it was flung into the Oort Cloud. If that's correct, Webb isn't just reading material preserved inside the cloud. It may be detecting a chemical fingerprint that predates the cloud itself. That makes these first-time visitors extraordinarily valuable. Having spent billions of years in deep freeze, they preserve some of the oldest surviving chemical records from the solar system's infancy. Some of those records might have begun before the Oort Cloud took shape. But not every clue comes from inbound comets. Sedna is a small reddish world. It never comes closer than about 76 astronomical units from the Sun, more than twice Neptune's distance. One trip around the Sun takes roughly 11,400 years. The last time it was this close to it, humans were only beginning the transition from the Ice Age to the first farming communities. That unusual path places Sedna in a transition zone between the Kuiper Belt and the Oort Cloud proper, a region some scientists call the inner Oort Cloud. Unlike the roughly spherical outer cloud, this inner region is thought to retain a more flattened shape, preserving some memory of the disk from which the solar system formed. It may represent a population of objects scattered outward early in the solar system's history, and later locked into stable intermediate orbits. What makes Sedna valuable is exactly what makes it strange. It's too far from the Sun to feel its warmth. A world that cold, that far out, should have kept its original surface untouched. It didn't. When Webb looked at Sedna in infrared light, the methane astronomers expected to find was gone from the surface. Instead, it revealed ethane, acetylene, ethylene, and water ice. The hydrocarbons are thought to have formed as radiation-altered methane over billions of years. Sedna's surface isn't a preserved record of what it was made of. It's a record of everything that has happened to it since. None of this explains why the Oort Cloud exists at all. For that, you have to go back to the beginning. What makes the Oort Cloud remarkable is not just its size, it is its age. To understand why the Oort Cloud exists, you have to go back 4.6 billion years. The young Sun was surrounded by a vast spinning disk of gas and dust, the raw material from which the planets were born. Closer to the Sun, that material was rapidly transformed, colliding, melting, and merging into the rocky worlds and giant planets we know today. But farther out, not everything found a permanent home. As the giant planets grew, their immense gravity flung countless icy bodies into deep space. Most were lost forever. Others remained bound to the Sun, settling over millions of years into the enormous distant reservoir we now call the Oort Cloud. Those scattered objects have spent most of the solar system's history in deep freeze, bathed in only the faintest sunlight. Time has left its mark on them, but far more gently than on the worlds of the inner solar system, allowing many of their ancient chemical signatures to survive. They are not remnants shaped by 4.6 billion years of geological processing. They are, in many cases, the original material, the same ices, gases, and organic compounds that existed before the planets finished forming. Every comet falling inward from those depths is a sample of that inventory. Webb is now reading those samples with a level of chemical detail that would have seemed impossible a decade ago. Water, carbon dioxide, carbon monoxide, organic molecules. Each one a clue to the solar system's earliest chapter. And the map is only beginning to take shape. In the coming years, the Vera C. Rubin Observatory is expected to discover thousands of new long-period comets that current surveys have missed. Each newly identified comet will be a potential target for Webb follow-up spectroscopy. That expanded sample will give scientists thousands of new chemical fingerprints to compare. Some comets may prove remarkably alike. Others may reveal unexpected differences that help explain how the outer solar system formed and how material was distributed during the birth of the planets. We've assumed the whole cloud is ours. It might not be. The discoveries of 1 I/Oumuamua in 2017, 2 I/Borisov in 2019, and 3 I/Atlas in 2025 confirmed that objects from other star systems do pass through our solar system. Scientists are now asking an even bigger question. Could some of these interstellar visitors have been captured by the Sun's gravity instead of simply passing through? If so, they could still be orbiting within the Oort Cloud today, mixed in with objects that formed in our own solar system. Right now, there's no reliable way to tell them apart. It has not been confirmed. But if it is eventually supported, the Oort Cloud would not just preserve the history of our own solar system. It might hold fragments from other planetary systems, carried here across the Milky Way. The Oort Cloud will almost certainly never be directly imaged. Its objects are too cold, too dark, and too widely separated for any instrument currently foreseeable. Its existence will likely remain inferred rather than directly observed for decades to come, known through the behavior of the comets it sends inward. But those comets are speaking. And for the first time, we have an instrument sensitive enough to understand what they are saying. Webb is reading chemistry that has been frozen in storage at the edge of the solar system for longer than complex life has existed on Earth. Each detection is a small piece of something much larger, a frozen archive of the solar system's beginning, sending its messengers inward one by one. The solar system formed 4.6 billion years ago. The record of that moment still exists, wrapped around everything we know, waiting in the dark. We are only just beginning to open it.